are intervening between A and B. 1, 2, 3. Therefore, it is 3. Carbon 13, H. What would that be? CH. And what would this be? 1. Because the 1 coupling. So whenever you write this J and then you write some elements out there, you're talking of the coupling between those two. But the number to the top left actually tells me the number of bonds that are actually intervening between the two atoms, two nuclei that are actually coupling. So 3 bond, 2 bond, 1 bond coupling and so on. So the NMR coupling has to actually operate through the mediation of the agency of the electrons, and it is actually spread over 1, 2 or 3 bonds. But what's the nice thing about electrons? Electron is a spin of half, and that's the reason why IISER works. And let's say when I come to hydrogen, what's the spin of the hydrogen nuclei? That's half. So is it not possible for this spin and this nuclear spin to couple? Yes, it is possible. And it's going to be even stronger. Why is it going to be stronger? Because unlike nuclei, which have to couple over a distance, the electron actually steps onto the nucleus almost, and therefore the coupling is going to be that much stronger. Therefore, when I look at the IISER spectrum, the IISER spectrum is actually going to be affected by the fact that this electron visits this hydrogen, can have a plus half or minus half spin, the hydrogen. Visits this hydrogen, this one can have a plus half or minus half. Visits this, which also can have a plus half or a minus half. So the 3 protons, how many possible combinations can I have if there are 3 protons? 4 possible combinations. We saw that, right? 3 equivalent protons, 4 splits. Why? It is up, down, down, 3 possibilities. Up, down, down, 3 possibilities. And all 3 down, 1 possibility. 1:3:3:1. So if I have 3 protons, they will have 4 possible combinations in which you can write them. And therefore, when this electron visits this, it can actually sample one of these possible cases. So what will happen to this electron now? It will have this broad feature which on derivatization you see this. How many features should I see for this electron now? I should actually see 4. Just like 3 protons will split an adjacent proton into 4 peaks because of its possible orientation, 3 protons can actually split the electron spectra also by 4. Because I still have the same 4 possibilities. Okay, and the third one is, right? We want these 4 possibilities. And these 4 possibilities exist over here. It is these 3 giving these 4 possibilities that are splitting the adjacent proton. So these 3 with these 4 possibilities can now split the electron which is visiting these protons now and then. And therefore, the IISER spectrum of metal radical will not be one broad peak which on derivatization should give me one peak like this. What will it be actually? It will be split into 4. And in what intensity ratio? 1:3:3:1. Again, just like NMR. So if you know how the 3 protons split the adjacent proton into 4 peaks with the intensity ratio of 1:3:3:1, immediately you must be in a position to say, well, that's the same thing I expect for the electron. And what does the IISER spectrum of the metal radical actually look like? So immediately what do I know? That this radical is actually visiting 3 equivalent protons, and that's the reason why I get this. What will happen if I have 2 non-equivalent protons? We won't do that, but you must be able to guess and tell me. If I have 2 non-equivalent protons, what would happen? If one splits into a triplet, the other one splits into a doublet, what would I have? A triplet of a doublet, and therefore the IISER spectrum should actually show me a triplet of a doublet. We know that in NMR, so I will just assume that we expect to see this in IISER. We will not go and bother ourselves with it. We look at the simple cases, and as I said, since you know NMR, I just want to highlight all those simple, straightforward comparisons which should immediately make you aware of what the IISER spectrum should really look like and what information you can draw from the IISER. So this is going to be my spectrum of this metal radical. Now tell me one thing. That splitting, what will it be dependent on? If it is big, what does it mean? If it is very small, what does it mean? If it is big, what does it mean? It means the electron and the nucleus are coupling quite hard. Very strong coupling. If the coupling is quite strong, splitting is quite large. If the coupling is very weak, they get very close. If there is no coupling at all, then I will not have the split in the first place. So the coupling is an indication of the split is an indication of the coupling, and the extent of split must be an indication of the extent of coupling. That's straightforward. What's the extent of coupling going to depend on? When will I have a large coupling? When will I have a small coupling? Any ideas? When will I have a large coupling? Electron nuclear coupling. When will it be large? Mind you, the electron is visiting on these protons, right? It's visiting the entire molecule. It's also visiting carbon now and then. So the lone electron is visiting carbon now and then. How do you know that? You can calculate the wave function and calculate psi square at each point, and that will tell you what the probability density is at any given point. Just like in a particle in a box. That's your wave function, right? If I square it, what does it mean? That's the probability density. And what does this really tell me? It really tells me how much of the time this guy is spending here, how much of the time this guy is spending here, and so on. So how much time it visits each part of the box is what is given to me by the square of the wave function multiplied by the volume. Likewise, if I go and get the molecular orbital in which the electron is residing, get the wave function, square it, and then start finding out what the square of the wave function is really at each point over here, what will I get? I will essentially get the probability of finding the electrons in those places. If the probability is very large, let us say the probability is very large at carbon, what does it mean? It means the electron on its motion is most of the time spending its time on carbon. It visits hydrogen now and then, but most of the time it is spending its time on carbon. If, however, I find that the probability density is very large on hydrogen and not on carbon, it simply means it goes to the hydrogen and sits there for a while, goes to carbon for a very short period of time, and again moves to some other hydrogen. In essence, what I am really getting from quantum mechanics, from the psi square plot, is actually the time that the electron spends on the different parts of the molecule. So, if the electron spends a lot of time on hydrogen, what do you think will happen? It will actually couple quite strongly because it is spending more time over there, and therefore the coupling will be strong. But if the electron does not spend as much time on hydrogen, but spends much less time on hydrogen and lots of time on carbon, what will happen to the coupling? Well, it will be weaker. So in other words, the coupling that I see in ESR is actually a measure of how much time the electron is spending on the nucleus which is actually coupling it. Stronger the coupling, more time it spends on these protons. Less the coupling, the less time it spends. So you can see ESR is giving me very powerful information on what is really happening to that one electron. Where is it spending its time on? And why would you need that information? Supposing I find that the electron is spending its time, let's say 85% of this time, which eventually happens to be the case, on carbon, what does it mean? It means the electron density is actually concentrated over here. If I know the electron density is concentrated over here, what does that actually imply? It implies there's an electrophilic center. So if I have a nucleophilic system, where is it going to attack? It's going to attack right here because I know the electron is actually spending, let's say, 85% of its time, and therefore the negative charge density is actually concentrated right here. In other words, you start getting information on things that you wanted to use in organic chemistry. For example, if I had a phenyl radical, I want to know where the phenyl electron in the phenyl radical is actually located, so that I can then decide whether I should do an electrophilic reaction and would it really hit one of the carbons or not. For that, I need to know whether the electron is spending sufficient time on the carbons or not. Well, I can do one thing, do an ESR and find out how much the electron is spending its time on the hydrogens and how much it is spending its time on the carbons. I will therefore get a picture. Is carbon doing anything as far as splitting is concerned? No. Because what is the spin of carbon? 0. So carbon is not going to give me any information basically. But who is giving me the information? The hydrogens, because they have a spin half And therefore, when the electron visits hydrogen, it splits, and this splitting is essentially information on how much time the electron spends on hydrogen. If I know how much time it spends on hydrogen, the balance of the time it must spend on carbon, and therefore I indirectly get information on what the electron density on carbon is. And that's how ESR comes in quite handy. Let's do a very simple problem, and we will see how this can be done. It turns out there's an equation that actually relates to splitting A. I know it is proportional to electron density, right? Greater the electron density on that nucleus, greater is the splitting. Less the electron density, less is the splitting. Therefore, it is very meaningful to write that that splitting is actually a function of the electron density on the nucleus, which is actually causing it to split. And therefore, I remove this for a constant. Now the question is, how do I evaluate that constant? If I know how to evaluate that constant, this equation actually becomes very, very powerful. Okay, how do I get this? What I do is, I take hydrogen atom, and do an experiment with the SR of that. What do you think will happen to the electron in the case of the hydrogen? There's only one nuclei with spin half, so how many peaks will the ESR spectrum of that electron will be split into? Yeah, there's one electron, there's only one, I know there's one electron on it. And what is this one electron doing? It's visiting the hydrogen on there. Of course, you also have learned that the s electron density at the nucleus is pretty reasonable. The p electrons actually have a node out there. So if the electron is in the p orbital, it really doesn't get very close to the nucleus. So again, it will double change the coupling constant. So if I can't get very close to the nucleus in one case, and in the other orbital I can get very close to the nucleus, I actually change my coupling constant. All this information will come out of ESR. But here is my electron. It's an s electron. Therefore, can get very close to the nucleus. What is the spin of the nucleus? Half. There will be one nucleus. So, how many peaks will it split the ESR by? One proton will split it into two. We learned that in NMR. If I only have one neighbor, it splits the adjoining peaks into two. So, this ESR spectrum of this electron will be split by this proton into two ESR peaks. What will that look like? Two peaks. And what is the splitting of this peak going to depend on? It is going to depend on the electron density visiting this nucleus. And if I remember right, I think it is 2.5 to 10⁻³ Here we always give in Tesla. You remember the experiment I said? You keep the frequency constant and move the field, and then you see where the resonances are hit. That's what you do over here. You keep the frequency constant and you change the field. And it turns out that to go from this resonance to this resonance, you actually have to travel through about 2.5 millitesla. Okay. So 2.5 millitesla is actually the splitting that I will see for the hydrogen atom. And that is my A. I don't know R. But what is the electron density in hydrogen? There's only one electron. And where is the one electron? It's on the hydrogen. So this experiment, or this molecule, this atom, I know the electron density, and the electron density is 1. The electron is spending its time on hydrogen, and therefore rho has to be equal to 1. So what does the R therefore become equal to? The constant which couples these two. That has to be equal to 0.05. If you actually, I think it's 5 millitesla, not 2.5. I think it's 0.05 Tesla. So therefore R actually turns out to be 0.05 Tesla. And how do I know that? I know that because I do the hydrogen experiment as a calibration. In the case of hydrogen, I know what the split is, 0.05 Tesla, and I know what the electron density is. And what's the electron density? It's simply 1, and therefore I can get the value of R. I can now use this value of R for any other system and then be able to find out what the electron density is. I think in the case of metal radical, this is 2.5 millitesla. If I know this is 2.5 millitesla, what's the electron density on these hydrogen atoms given by? It's simply going to be equal to 2.5 millitesla equal to 0.05 into rho. I don't know rho. And what is rho? It's the electron density on the hydrogen. Why on the hydrogen? Because it's the hydrogen that is causing the splitting. Therefore, this density must really refer to the electron density on this hydrogen. I know from experiment that the splitting is 2.5 millitesla. I know the value of R from the hydrogen experiment to be 0.05. Therefore, if I use this equation, what will I get? I will actually get rho of the electron density on this hydrogen with regard to this one electron, meaning that this one electron is actually spending its time on these three hydrogens given by this equation. If you work this out, it will actually turn out that rho will be equal to, I think, 0.48 or thereabout. Now this is how much? About 0.05. No. Yeah. So it's 0.05 on this hydrogen, 0.05 on this hydrogen, and 0.05